2 times minus 1 over 2 pi I integral boundary d f of w over w minus z to the power 4 dw.
Shouldn't the coefficients all be positive?
We
The chain rule gives you a negative sign, but you also have negative power, so there's essentially in all cases.
You might be right. Let's see here. Yes, thank you. Thank you. You're right. I'm thinking of the minus I'm thinking of keeping is from something else. But you're right. I neglected. There's the one minus from the power, and there's the other minus from the chain rule, which means that I just get a plus. Very good. Thank you. This would have dawned on me as soon as I got back to my notes. But anyway, so apparently this. Oh man, 2 times 1, and of course we can trade this out for a 3 times 2 times 1, right? And I think you see where this is going. If we calculate the mth derivative, right, of z, what's it going to give us? It's going to give us m factorial divided by 2 pi I integral over the boundary of d of f of w dw over w minus z to the, well, apparently m plus 1. And this, my friends, is the generalized Cauchy integral formula. So if you're up against integrating, so basically here's what you use it for. If you're integrating something that's like holomorphic everywhere, right? And you're just taking that thing and you're dividing by, you know, some power, like z minus, you know, w minus this to some power, then you can just do this. And I think it's helpful to rewrite this theorem in other letters. So like, I think about it this way sometimes. If I have 2 pi I, the mth derivative of z naught, divided by m factorial, that is equal to the integral over the boundary of d of f of z dz over z minus z naught to the m plus 1. I usually like this format of the theorem to actually calculate things. That's just a more, because we usually got to give you problems in integrals of z, right? Let's take it for a spin, right? What if you want to integrate, say, you know, Cauchy of z divided by, oh, I don't know, z, I like I, z minus I to the third power. And the Cauchy of z is too boring. Let's make it Cauchy of z squared. We'll appreciate that in a second here. And we'll do this, oh, I don't know, say over the circle of radius 4. Okay? So, as long as that circle encloses the place where you have division by 0, we're good. If instead of putting modulus of z equals to 4 for my curve, suppose instead of that I did like modulus of z equals to 1/2. If I did that, then this would just be integrating to 0 by Cauchy's theorem. Because this function, right, where does it have a singularity? It has a singularity at I. Right? So if I was integrating around this half radius circle, I would have that expression is holomorphic on the entire disk, the red disk here. And I just fall back on just the plain old Cauchy's theorem, integrates to 0. Yay, done. But if I is inside there, then I need Cauchy's generalized integral formula, which in this case I've got m equals to, now here's where it gets tricky. What is m equal to? 2, all right. Which means apparently I need to say 2 pi I divided by 2, right? times the second derivative of cosh of z squared, right? Evaluate that thing at z equals to I, right? So what is the second derivative? It's the derivative of the first derivative. The first derivative is 2z sinh z squared, right? And then what do I got? Well, I got pi I. This differentiates to 2 sinh z squared plus 4 z squared cosh z squared. And I have to still evaluate as z equals to I. Plug in z equal to I, what do I got? Well, pi I, 2 times the sinh of minus 1 plus 4 times minus 1 cosh of minus 1. And I guess I can clean it up a bit. So I got myself like pi I times, I'll put a minus up front, minus pi I times 2 times the sinh of 1 plus 4 times the cosh of 1. And you might be able to simplify it further. I don't really care. That's good enough for me. It really didn't take us very long to get from, looking at how to calculate these in terms of parametrizing integrals to kind of supplanting all that, right? These theorems do some very heavy lifting for us by like parametrizing the thing we're interested in once and then making use of it. It's very sneaky. Now, this is still not the most, it's not the ultimate form, right? Like, what we're looking at right now, it's like, it might be like Super Saiyan, like maybe Super Saiyan 2, maybe. The Ultra Instinct, it comes much later. It comes later.
Yep.
What?
Me and Jeff were talking about when we were preparing for the test. We were studying and we were watching Goku's transformation.
I skipped right past Super Saiyan 4 because that one's just dumb. It's here.
This is what it looks like to go even further. To go beyond.
Yeah, yeah.
And then you weren't here, but right before the test, I started going Super Saiyan.
Yes, I think you showed up
I made
late
some
on the
fun.
test.
I tell you, we used to joke that if you looked at my friend Paul's head during a test, you could see a faint yellow glow. But that was after he dropped his mechanical engineering major and his true form was revealed. I was hanging with Paul before he did that. And then I couldn't touch him. He was just, he was just phenomenally powerful with classical mechanics.
Doctors framing us as he went to the dark side.
Well, that's one viewpoint, I suppose. So here, if you look at my notes, what follows here is about 2 pages of algebra to prove that this is true, which is the next step. It's m equals 1 Cauchy integral formula, right? So here's so that was actually just the induction step, m equals 1 induction step. Here's the induction, I'm assuming inductively the formula holds for m. This calculation, blah, 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 I won't subject you to it except to show it to you, is proving the induction step, which then you can establish Cauchy's generalized integral formula for arbitrary integers. And it's binomial theorem, and it's fun calculation, and everybody should do it once if you're going to be a math professor, but if you're not, well, it's probably okay to skip it. And, but don't skip this. This is our lifeblood right now, until we get the Ultra Instinct, at which point this will be like just stupid. because we won't have to work at it anymore. Once we have the ultra instinct, it will effortlessly come to us. We will just do the integrals. And we won't tire. We'll just keep doing them. And we'll just do them all day long, and they will never tire us out. We'll just, because it will be instinctual. But we're not there yet. We're not there yet. We'll get there. Now here is an example that's kind of interesting. I have 1 over z minus I to the 6th power. So if the integral over the unit circle radius 2 there, so you got to be careful, guys, right? Whenever you're faced with one of these problems, you got to ask yourself the question, is this really a problem where I'm supposed to be applying the generalized integral formula, or is Dr. Cook just messing with me and it's 0? You got to ask yourself that question, because just because it looks like it doesn't mean that I wouldn't mess with you and just put the circle in circle bounding a space where the function's holomorphic, in which case it's just 0. Now that's not the case here, because z equals to I is within the circle of radius 2, right? So this is an honest to goodness, apply the generalized Cauchy integral formula, this time with m equals to 5. And well, I am sure glad that this wasn't a sine of z squared, because if that was z squared, and we had to differentiate sine of z squared 5 times, that would be a lot of product rules, like a lot. But it was sine of 2z, so when you differentiate that 5 full times, you just get back to minus the cosine, and you get it, you get 2 times 2 times 2 times 2 times 2 times 2 5 times, otherwise known as 32, and there you go, answer. Now this one down here is more funky, because it's got some kind of fussy issues here, in the sense that if I'm looking at z to the 4th plus I equals to 0, like where does that have zeros? Well, it has zeros at like e to the pi I over 8, minus pi over 8, and these four places where you have that z to the 4th plus I is 0, right? So if I integrate around this blue circle, and I have like a z to the 4th plus I in the denominator or something, then I've got to watch out for just one of them, right? See, because only the red dot is actually in the interior of the blue circle. So as I integrate something with the reciprocal of z to the 4th plus I only need to worry about the red dot, which is what I have down here. And I know it looks hideous, but it's actually not that bad what's going on here. I've just factored z to the 4th plus I, and the only thing here that actually matters to the integral is the red dot, which is the e to the minus I pi over 8. That's this one, right? All of this mess over here, 1 over this, is holomorphic on the blue circle. So that's playing the role of the function in the Cauchy's generalized integral formula, which is why all I do with all of this is just to plug in the center point of the circle, namely that, into those, which gives me this, which gives me this, which gives me that. Which of course you could clean up, but cosines and sines. But anyway, so your next, like mission 5 will be these kinds of calculations, okay, like a lot of this. And finally, I would regret my life if I didn't make this final parting comment. Notice that this generalized Cauchy integral formula says something. It says that if you have a function, right? If you have a function, can you move over for me? Thanks. If you have a function, you can integrate it, right? But also, it's equal to its mth derivative. What does that say? It says that the mth derivative exists if the function can be integrated. When can the function be integrated? It's holomorphic and continuously differentiable in our current setup, right? This means that there are no complex functions which just have one derivative. Like in the real case, we could have a real function which has one real derivative but not two. We could have a real function which is differentiable but not continuously differentiable. Apparently, in this case, if I have one continuous derivative, I must have infinitely many. Next week, next class, I will prove to you that if we even have complex differentiable, that implies continuously complex differentiable. This is the content of something called Gorsaz's theorem and Morera's theorem, which I will prove next class most likely. So that doesn't really give us any new computations. It is purely of theoretical interest. So if you want to skip a class, that's the one to skip. Anyway, I'm joking. Don't skip classes.